Yes, hi guys. So today I'm talking about volume of solids by integrals, multiple integrals. Now in this case, there are two types of multiple integrals. We know about double integral and triple integral. With the help of double integral and triple integral, I'll talk about that how to find out volume of a solid. Okay, or any figure what is given to us. So I have to talk about first by double integration, the volume of solids. Let me write here the first of volume of solids by double integrals. This is under the multiple integral, so the same thing by double integral. First I'll talk about how to find out the integral, and then second part is volume of solids by triple integral. Volume of solids by triple integral. Triple integrals. These are the two topics today. So volume of solids by these integrals, multiple integrals. So okay, this is the today's topic, and all these questions are based upon triple integration or volume of integration by double integral or other or by triple integral. First, let me describe it how to find out volume of a solid by double integral first, and then triple integral. So I talk about first by double integral. Suppose we have there is solid figure. We have three-dimensional figure here. We take this is x, this is y, and this is z axis. Okay, and this is origin. Okay, this is origin. Now, if I find out that if there is a solid, okay, which is here we have the plane z equal to 0, but z equal to 0 is on this plane. So if I take z equal to 0 on this plane, okay, and if z equal to 7, this is the first topic here, first condition. Okay, volume of solids by double integral. First I am talking about by double integrals. Okay, first by double integral, how to find out? Okay, now if I find a projection of on the x-axis, x by axis, let me take here, let z, the variable z is equal to fxy, or z is a function of xy. Okay. Then if I draw a cylinder, for example, let me take here, there is a cylindrical figure. This is straight line. Sorry, this is a proper straight line, and this is the projection on the x by axis. This is x by axis. On this x by axis, z equal to 0. Okay. So first of all, we have to find out what is elementary area of this figure. This is nothing but dx dy, we can say, or elementary, or we can take delta x delta y, area of this figure, because this is and a line parallel to this. I mean, this is the strip. We can take a small strip parallel to the z axis. This is the z. Let me take this is length is z. Okay. So what is the area of this whole cylinder? I mean, this cylinder, this elementary cylinder here, it will be z into delta x delta y. Area of this whole cylinder, I'm sorry, volume. This is volume. The volume of this whole cylinder, because area is delta x delta y in the shadow portion. Now let me take here of this circular with top. There is circular base here. This is the projection of this. Let me take this is surface here A. This is A dash B. The surface A dash area A dash. This is A here. So the projection of this A. But here we have x equal to 0 in this plane. In this plane y equal to 0. But we have to find out what is the volume of elementary figure. Like this is, suppose we have taken element here, which is the area of which is delta x delta y, or this is the element figure here, and then we draw a cylindrical figure like this, having z as the length. These two generators are there. These two generators are forming this body, or this elementary cylinder here. Z is the or we can say there are two parallel generators, this one and this one, the length of which is z. So z into this length or height into area of the base, the volume of the cylinder. Volume of the cylinder is area of the base into height, but height here is z. Z into delta x delta y is the volume of it. Therefore, volume of the figure, let me write here. Here, volume of the elementary cylinder, cylindrical shape or cylinder here. Elementary cylinder is equal to small z into delta x delta y, or which is delta x. Delta x delta y is very small bit. This is the volume of the elementary cylinder. Why? Because z is the length of the cylinder and area is the delta x delta y, or this delta. This is, when we summarize this is equal to then dx/dy. Okay, so this is z into delta x delta y, the area of this base, and then length or height, or area into area of the base into height is will give just the volume of the cylinder. We know that what is the area of the cylinder, of the base of the cylinder, pi r square. This is circular here, and into h, pi r square h is the volume of the cylinder. We know, but we have suppose we are indicating this by dx/dy. So the area of the base is of dx/dy, because it is in the xy plane. The shadow portion of this plane, I mean this shadow or projection of this shadow, is on the xy axis. On the xy axis we have the elementary figure, the area of which is delta x delta y. This is the volume of the elementary cylinder here. Total, therefore total volume of the solid here, total volume of the solid, this whole solid which is given to us. And if I take very small element here, if there is a, suppose there is a figure here, cuboid type, then this is cuboid type of figure, so total volume of the solid is equal to, we write here double integral sign, which is upon this area. Let me take this A dash area and A dash here. Okay, so with respect to A dash area, or we draw here two parallel lines with parallel to x axis and y axis. Okay, with parallel to x axis and parallel to y axis, we can find out the limits of y and x. We can find out limits of y and x. This will give us z into dx/dy, which is nothing but, if suppose we have found out the limits here, this z is fx by here we have taken. If I take, so z is a function in this case of x and y, so dx into dy. This is the total volume in double integral. Now, what are the limits of this? X limits, maybe first are the x limits, and second is the symbol of integration is for y limits. We put here x limits under the proper limits of the whole body, so that the whole body can cover, the whole solid can be covered. Okay, here limits for x and y, limits for x and y are chosen for integration, so that the whole solid is covered, so that the whole solid figure or solid is combined or is bounded. Let me take, is combined or is bounded, or total solid is covered. So for that we have to find out the limits here of x variable, y variable in this case. Now if I take, suppose there is, here it is z equal to 0, so we are having this element which is lying in the xy plane. But suppose this plane is lying in the, or this figure, this element is lying in, sorry, and if I think that this element is lying in the other planes, then what is the volume? This is the process I'm talking about, how to find out volume into or double integrals by double integrals. So second part of this, okay, here volume of a solid okay, having x equal to 0, let me check. X equal to 0, and the function, if I take here, we have taken here, okay, x equal to 0 and x equal to, let me take f, y and z. Here x is a function of y and z, and x is 0. Where is x is 0? If I take here, let me take this not x, so that we can, this is not z. Let me take from this x and y. Please suppose x here, this is y, this is z. This is x and this is z here. Or let me take, this is x here, this is y and this is z here. Now it's okay. Now here in this case, this is co-origin x, y, z in anti-clockwise. I've taken here. This is in anti-clockwise direction. We have taken these, we have chosen these directions, I mean these coordinate axes. In the coordinate axis, x, y, z is there. Now in this plane, we have again x equal to 0. Here, the function x is equal to fx, x or y, z. But here, x is a function of y and z variables. So this is again, let me take, here there is a cylindrical figure. I have draw a cylinder on the elementary, this element here. Now in this case, this is the length x here, this height is x here, and this area of the base, again I've taken this, suppose a, this is a dash, with respect to this a dash, which is area of this element, of this elementary figure here, which is, let me take delta by delta z. In this case, area of this element, area is equal to delta by delta z, because it is in y-z axis, y-z plane. Y-z plane we are having. If we draw parallel lines parallel to y-axis and parallel to z-axis, then we can find out what are the limits for y and z coordinates. Okay, and this length is x here. Okay, x. If generate lines are down here, a cylinder is formed. What is the volume of the cylinder now? Volume of the cylinder in this case. So, we'll have, first let me find out what is the volume of the elementary cylinder. Volume of the elementary cylinder. Oh, this is keyboard. Let me take the keyboard here. First keyboard, then cylinder. We have drawn a cylinder here. So this is nothing. Again, this is x into. This is x here. Okay, where x equal to 0. But this is x into delta y delta z. Where x is f by z into delta y delta z. Therefore, total volume of the solid to cover the whole solid. I mean, whatever solid is given to us, that we find out here. So, the total volume of the solid given is equal to, in this case we are finding out by dual integral. Okay, this is area a dash. In this case, area a dash is defined in y z axis. This is y z axis, y and z. Here the integral signs for y, and this is for z, or z and y. That doesn't matter. So this is x into delta, sorry, d by d. This is d by dz now. D by dz, which is a dash for this integration is double integration defined on the y z axis, y z plane, and this is x is f y z into d by dz. So this is the volume of the solid in y-z plane. If it is lying in the y-z plane, the shadow of this figure, the shadow of this is on the projection of the y-z axis. Here we are having this x is the length of this cylinder or height of the cylinder. In this case, x into this area of the base will give us the volume here. X into d by dz is the volume of this element, but we integrate this, summarize this whole, that will give us the volume of the whole solid element. Okay, this is in y-z axis, y-z plane. Now we are debating y equal to 0. Third possibility maybe, there is third possibility now. What is the third possibility of double integral? Third possibility, the volume of a solid, okay, in y equals to 0 plane, I equal to 0 plane. In this case, let me take this as when y is 0. If this is, let me take x here, okay, this is x here, this is y here, this is z here. They are the axes. The three axes are there. This is xz plane or zx plane. In xz plane now, again we will have this xz plane. This is delta x delta z. Okay, this is elementary area. Okay, and here y equal to 0. In this plane, we know that y coordinate is 0 in zx or xz plane or zx plane. This is zx plane here. Delta z delta x or delta x delta y, delta z sorry, delta x delta z or delta z delta x doesn't matter. For this is the material. Now this is the plane y equal to 0. Now this length is in this case y. This length of this height is, or this line is parallel to the axis of y. Axis of y parallel to the axis of y. So this is y coordinate, or along whatever length is given to us. I mean this height is given to us, that is y coordinate. That is equivalent to y coordinate. Volume of the element. So volume of the element. Volume of the elementary is figure of solid is equal to, here in this case, first let me write y here. This is y into delta x delta z or delta z with y z x. In that way we can write delta x into delta z. That means, okay, this is elementary volume of this element here. This element in height or length, area of this is delta x delta z into y. This is elementary. In case of plane y to 0, this is plane is y to 0. Y to 0 in this zx plane. This is how total, therefore total volume of the cylinder here y equal to f x z. The total volume of the solid may be any cylinder, sphere, it may be, or cuboid, okay, or it may be a cube, etc. Cuboid, cylinder, cone, okay, or a sphere, hemisphere, that may be there. That is doesn't matter. That is not limited to only cylinders or something. We are taking cylinder here, but maybe a sphere, a hemisphere, maybe cone, etc. That I'm taking only symbolical example here. Okay, question here. This is total volume of the solid given will be equal to double integral sign. This is again a dash upon this is a here. This is a dash upon a dash. It is defined. A dash means zx plane or x z plane here. For x this is for z, or this is for z, this is for x. Doesn't matter. This is now y into sorry dx dz. Dx dz. This may be further defined as y is here f x z into dx dz. This is the volume of the whole cylinder. Now limits are chosen in such a manner that the whole solid is covered. Whatever solid is given to us, whatever equation of the solid is given to us, that is completely covered, so that we can cover, we can take limits for the variable x and variable z in this case, or it may be x and y and z, z and x, whatever. This is how we have to find out the help of double integral. This is the way of finding out volume with the help of double integral. Volume of solid with the help of double integrals. Now we can take triple integral. Second case, sorry, this major second case, there are three possibilities in this case. But in case of triple integral, not 3 dimension, 3 dimension figure of all the solids, there are 3 dimensional figures. Now volume of solids by triple integral. Now in this case, okay, volume by triple integral. The third case is by triple integral. What we take here. Now in this case, the elementary. What is the element cube here? Let me take cube here. There is a cube here or cubical surface. Let me take this, the cube surface. Anywhere it can be. This is the x, y, and this is z. Let me take an octant of this. So this is the sphere. Then the octant of this sphere in 3-dimensional figure. Okay, and the area of this is delta x, delta y, delta z. Area of this elementary octant. Okay. Therefore, is volume of an elementary. Let me take here a keyboard shape. A small element here is keyboardal shape. Okay. And if I take that keyboardal shape here, okay, let me take this as keyboardal shape here. I'm sorry. This is keyboardal shape. So this cube, this one, this is delta S, delta Y, delta Z. The volume of this smaller part, this is the volume of an elementary cuboid. In this case, we are taking cuboid. Okay, so elementary cuboid is equal to delta F, delta Y, delta Z. Therefore, total volume of the solid will be given by triple integral sign, or this one volume integral. Okay, triple integral. This is dx, dy, dz. So this is area of one elementary cuboid, and triple integral sign will summarize the whole solid given. The complete solid will be covered by taking this integral sign or triple integral sign with respect to x, with respect to y, with respect to z. So limits are given in variable x, variable y, variable z. Then the whole solid will be covered. This is how volume of a cuboid or a 3-dimensional figure is found out. I mean, a solid is found out with the help of triple integral sign. So triple integral sign is used with the limits of integration. We have to find out the whole. Here, again here, limits are the limits for integration of integration. Limits of integration or for integration are chosen in such a manner so that the whole solid is covered or is combined. The whole solid is covered. Okay, so that the complete solid is bounded or is covered, is completed. So in this way, the volume of cylinder, volume of any figure is with the help of triple integral. We have to use the triple integral sign. That is the point here. If I take z, limits are z1 to z2. If I take here limits for z1 variable z1 to z2, then this one is there. Okay, so z1 is completed. Then we write here z1 minus z2 or z2 minus z1. We integrate this first with respect to z. Then dx dy will be left over. So then the double integral will be used. So this is first integration. That means first integrate with respect to z here. This will be z only. In place of z, we have write the limits. This is double integral. It will be z2 minus z1. Integrating with respect to z, it will be z only. Okay, now double integral sign is left over. The first integral sign is completed. This is z2 minus z1. After substituting the upper limits and minus lower limits in place of z, the integration with respect to z will be only z area. z variable. In case of z variable, we are substituting upper limit minus lower limit z1 z1 into dx dy now back to double integral. Okay, in this way we reduce this into limits. Finally, the limits for with respect to x variable we can put in the end. After this, we have to integrate this with respect to y. After that, putting the limits for y variable, then finally integrate with respect to x. Then final x limits are put in the solid, and the complete volume of it is calculated. Finally, volume of the given solid is obtained. So this is the process how we find the volume of solids. Okay, by double integral, by triple integral, using these symbols. Now let me take questions here. These questions will give us a complete knowledge regarding how to find out volume of a solid with the help of double integral or triple integral. That is the point here. Because double integral and triple integral are only included, no other integration signs. Oh, okay, no 4 times integral, quadrilateral integral or. So let me take now questions. These questions are taken, only 10 questions are taken of volumes. But questions are many. But the students have asked me a number of questions, but it is impossible that I have to analyze the whole lecture series. But I know that my lecture series is very large. Okay, number of lectures are covered for a single topic, but that is going to just take the students step by step knowledge. Give the students knowledge, understanding of the knowledge of the topic step by step, so that they can get complete knowledge. Now come to and the volume of sphere. Now sphere is given to us, that's the provided result is going to be base. Okay, to find out what is the volume of this sphere. First question is here, volume of the sphere. To find, this is to find here volume of the sphere. What is that sphere here? Volume of the sphere, this is x sphere, y sphere plus z sphere equal to a sphere. Now in this case, if I find out the limits for z variable, okay, and x and y and z, that is how we have to take the volume integral here, volume of triple integral here, or double integral, that doesn't matter. If I take double integral, that is possible. Then we convert this whole into variable z is to be found out. Okay, so x variable, let me take the x variable. From this, if I substitute first z, what are the limits for z here? First, let me find out what this sphere is. Let me take. This is multiple integral. This is 3-dimensional geometry here. This is again y. This is x axis. This is z axis. If I take an octant here, so this is in the positive octant here. Find the volume of the sphere. To find out the volume of the sphere, we have to find out the one positive octant here. This is one octant. If I find out this is one octant, volume of this one octant. After that, multiply this by 8. Complete volume will be found out. Okay, so that will give us a complete volume of the whole. This is one of the octants, 8th part. So this is 3-dimensional figure. 3 in the height, 3 below this origin. Okay, so there are 8 parts of this. First octant is positive octant here in yz or yz axis, x y z axis. This axis maybe z we have taken like this. Okay, and this x and y is like this. So the base is here on the xy axis. Z is the height. In that way, we can find out the volume of this first limit. What are the limits here? Limits for x, y, z. Now in this y, z axis, x equal to 0, if I substitute x equal to 0, or if I take x, y axis, then z is 0 here. Z equal to, z limits are from 0 to a square minus x square minus y square. Let me take z limits. So limits for z. Limits for z are 0 to a square minus x square minus y square. Okay, this we have to take this x square y square to that side to give us a square minus x square minus y square. This is equal to z square. Z equal to under root of this, or this is under root of this square root of whole value. So for z square is there, z square equal to a square minus y square, but z equal to this. Limits for z variable are 0 to this. Initially, suppose z is 0 here in the xy axis, and then other upper limit will be obtained by this putting z equal to finding out this from given solution. Okay, so this is for z. Now let me take z is obtained. Now what is the y here? The y limits will be, and limits for y will be for y will be y equal to 0. Here y equal to, now we have to take x equal to y square equal to a square. So this is now y square equal to, or y equal to under this a square minus s square. The other limits here. Okay, and for x finally x equal to 0 to x equal to a, then x square equal to a square. This was 0 now, x equal to a. From 0 to a limits, so that the whole figure, all the octants are covered. In the first one, we are having this one octant, then 8 times of that octant will give us the whole area. Or if we have taken these limits in this way, then the complete area is cut with no need of multiplying by 8. So the total volume will be found out. So this is the process of finding out. When we multiply this by 8, then octant is given to us. So this is how we have to find out the area. Now let me put this area in the way of this kind. What is the volume of this by triple integration? If I found out double integration, if I found out by double integration, the z equal to this value, z equal to, we can put in the beginning, when double integral sign is substituted. Okay, so if I find out by double integral sign, okay, let me find out the volume of this by double integral and by triple integral. Using double integral, first process using double integral we have to find out by double integral. First volume by double integral. What we have to do here? Here z is equal to a square minus s square minus y square. This is the value of z value. Now we know that the volume